This is going to be a pretty quick video. We're just going to look at the properties of solutions. What is the solution process? How do you determine if it's endothermic or exothermic? What about solubility? What does saturated mean? What does unsaturated mean? And how do you find mass percent, mole fraction, and molarity? Let's take a quick look at the solution process. Homogeneous mixtures are solutions, and they can include solids, liquids, and gases. For example, dissolved oxygen in water. Remember that the solvent is the component that is in the greater amount. It's whatever we're putting the substance into to mix it up. Usually that's water. The solute is in the smaller quantity, and that could be a gas, solid, or liquid. So if you're making chocolate milk, milk would be your solvent, and the powdered Nesquik would be your solute. Now, a solution actually forms when one substance disperses uniformly throughout the other, and this depends upon two things. One, the natural tendency of substances to mix and spread into larger volumes, and the type of intermolecular forces that are going on in this process. Mixing of gases is a spontaneous process. Entropy increases. Just think about gases like kids at a park. Kids are running all over the place. More kids show up. They just mix spontaneously in total chaos. Mixing, like as in solutions, is usually spontaneous, but again, it really depends on the intermolecular forces and what else might be happening in that solution. Well, you can't have a unit on intermolecular forces and not discuss their role in solution formation. So let's just remember that solids and liquids are more governed by intermolecular forces than gases, and that's because they're so much closer together that those interactions occur more often. Well, there's three things happening in solution formation. The first is what we call solute-solute interactions, and this is the interaction between the solute particles. So let's say salt. What interaction's going on between this salt molecule and this salt molecule? Maybe not the best example, but you get the idea. The solvent interactions is what is happening between the solvent particles. Now here, I think you'll be able to picture it a little bit more clearly. Water, for example, is usually our solvent. Well, this water molecule likes this water molecule, and they're bonded by hydrogen bond. So we have some interactions going on there. And then lastly, you have to consider the solvent-solute interaction. How likely is it that the thing you're putting into the liquid wants to interact with it? So what does this mean? The solvent-solute interactions either need to be equal to or greater than the sum of the solute-solute, solvent-solvent interactions. So let me break this down really simply for you. And I know we've talked about it before in a lab, but let's review it here. Let's say we're wanting to dissolve salt in water. Three things have to happen. First, you've got sodium chloride. Ionic bond. You have a positive attracted to a negative. The first thing you have to do is break that sodium chloride ion up, or sodium chloride compound up into ions to make sodium ions and chloride ions. Number one. Number two, well, you've got these water molecules and they're bonded to each other through hydrogen bonding. You have to break that bond. You have to break that intermolecular force. So you've got to not only break the sodium chloride into its components, but you have to break apart the water molecules. Now those water molecules are free to encompass those ions. So you'll have water molecules surround the sodium ions, you'll have water molecules surround the chlorine ions. Now those water molecules will orient themselves differently so that the positive, negative attractions are lined up. So they'll look a little bit different in that hydration moment. But then you would actually have to kind of consider, okay, what's going on? How much energy did it take to break the sodium chloride up? How much energy did it take to pull those water molecules apart? And then how much energy was released when they came together? And this is basically Hess's law, as you can see on the equation. It just interacts how these three things work together. So if the H mix is greater than the solute and the solvent, it's going to be exothermic. So again, like dissolves like, so oil is not going to dissolve in water, but sodium chloride will dissolve in water because ionic and polar are very similar. But it ultimately comes down to these intermolecular forces and what's happening. Again, you have to be able to break the solute up, whatever that is. The solvent, you have to pull those molecules apart, and then those molecules have to surround your ions. And it really depends on how much energy it takes to do all the breaking versus how much energy is released when the mix occurs. So let's assume that we've broken up the solute, we've pulled the solvent molecules apart, and we have some mixing going on. When a solute dissolves, sometimes it's going to crash into another dissolved solute particle, and it's going to become a solid again. We call this crystallization. When the rates of crystallization and dissolving are equal, we wind up in a dynamic equilibrium, and then no further solute will crystallize in solution. So let's look at some of these definitions. Solubility is just the maximum amount of solute that can dissolve in a given amount of solvent at a specific temperature, pressure, etc. And then unsaturated versus supersaturated. Well, unsaturated means that you're dissolving less solute than the amount needed to form a saturated solution. So let's say a solution can hold, I'm just throwing out a number, 10. And you're at 5. Well, you're unsaturated. You haven't reached the maximum amount that solution can hold. When you've gone beyond that number, so arbitrarily 10, you go beyond that, then the solution is supersaturated and it can no longer dissolve anything else. And we've done this in the lab. We've heated solutions, we've crushed the solute, we've stirred it to no end. And when you get to the point where no more will dissolve and it just starts to collect on the bottom, put a string in there, and what do you get? You get crystals. So unsaturated, you're nowhere near that point of saturation. Supersaturated, you've gone beyond. And then saturated is simply you've hit that maximum. Now that point can be kind of tricky, and we've talked about this before in a POGL. The problem with saturated solution is if you actually hit that point, you won't know that it's saturated because you know extra stuff will start falling out. Again, once you have dissolved the maximum and the chemicals start to collect on the bottom of your beaker, you're in supersaturated. So saturated is that pinpoint spot where you've put just enough in that it can't hold anymore. The moment you go beyond that, it's going to start to collect on the bottom. So you can't really see saturated solution in the lab, but theoretically, that's what it is. So what are all the factors that can affect how soluble something is? Well, the first is the solute-solvent interactions. The stronger the attractions between the solute and the solvent molecules, the greater the solubility of the solute in that solvent. Again, this goes back to that like dissolves like. When you hear the word miscible, it's liquids that mix with each other. Immiscible are liquids that do not mix with each other, like water and oil. Make sure you can recognize polar and nonpolar substances because polar dissolves polar, nonpolar dissolves nonpolar. Water, for example, we know is polar. Alcohols are polar, and you can recognize these because they're going to be a carbon-hydrogen chain with an OH group. So maybe CH3, CH2, CH2OH, something like that. And the bigger the CH chain, the less polar it's going to become. But now that this big, huge, long alcohol molecule is becoming nonpolar, the more likely it's going to dissolve in something that's not polar, like hexane. Just recall that solubility can be increased by increasing the number of polar groups. If you want something to become more dissolvable in a polar solution, have something with more OH groups, for example. Substances with similar intermolecular attractive forces tend to be soluble in one another. I've said that before, but also remember that ionic does behave like polar. So ionic substances will dissolve in polar substances. This is why salt dissolves in water. Network solids, though, like diamond and quartz, are not soluble at all. Just keep that in the back of your mind. Then we need to talk about pressure. Now, solubilities of solids and liquids are not affected by pressure above a solution because they're in the solution. But gases do depend upon that vapor pressure above a solution. As there's more vapor pressure above your beaker, it's pushing down, keeping that gas in the solution. So if that vapor pressure becomes less gas is going to want to stay dissolved. And that goes into something called Henry's law. Temperature also can affect solubility. Now with solids, if you increase the temperature, you're going to get more to dissolve. Have you ever tried to put sugar into iced tea versus hot tea? You can get more sugar into hot tea than you can into cold tea. Gases, though, are different. If you increase the temperature, more gases are going to escape the solution rather than stay in the solution. So a little bit of oppositeness going on there between gases and solids. And how can you have an AP unit without a little bit of math involved? Again, in this case, pretty simple. We've already discussed these, most of them at least. Mass percent is just the mass of a component divided by the total mass times 100. Now, when you're talking about solutions, a lot of times we're talking about parts per million, ppm, or parts per million or parts per billion. Again, those are pretty easy conversions you can do. A mole fraction just compares the moles of the component to the total moles of all components. And of course, the old standby molarity, moles of solute divided by liters of solution.